Section 5.3, the Fundamental Theorem of Calculus. As the name implies, there is one theorem, or two theorems actually, two parts of the same, that are fundamental to calculus. Now, the mean value theorem for definite integrals is not one of them, but we will start with this. It's very closely related to what we ended our last section with, which was finding the average value of a function. So let f of x be continuous over the interval a to b. Then there exists at least one point c in that interval, such that f of c equals 1 over b minus a times the integral from a to b of f of x dx. That is, there is at least one point such that the integral is equal to f average, the average value of the function. That's what that's saying. Now we can also write that as the integral from a to b of f of x dx is equal to f of c times b minus a for some c in that interval a to b. Now, sometimes we want to know what that value of c is. That is, at what x value is the average value occurring. So, with that in mind, example 1, find the average value of the function f of x equals 8 minus 2x over the interval 0 to 4, and find the c such that f of c equals the average value of the function. Go ahead, and we don't have a good way to find the value, the area of the integral there, the area underneath that function over an interval yet. So let's go ahead and graph this. At 0, the value is 8, and at a value of 4, which is our other endpoint, that is going to be 0. All right, so the area underneath that curve is a triangle, and that is going to be, all right, let's go ahead and write this. Integral from 0 to 4 of 8 minus 2x dx. The base is 4, the height is 8, divided by 2, which should be 16. Okay, so the area is 16, so the average value is going to be, I'm going to introduce the 1 over b minus a. All right, so times 1 over 4 minus 0, so that my average value, let's put that as a subscript, is equal to 4. So, what x value gives me an average value of 4? Let's go ahead and take f of c equals, that will be 8 minus 2c. We want to know where that equals 4. So really we're saying f of c equals 4. This just happens to be 8 minus 2c based on the definition of the function. Subtracting 8 from both sides and then dividing by negative 2, we should get a c value of 2. All right, so that is our point at which the average value is attained. All right, example 2. Given the integral from 0 to 3 of x squared dx equals 9, find c so that f of c equals the average value of f of x squared over 0 to 3. Well, my f average, or in our case, I'm just going to go ahead and write f of c, is going to equal 1 over b minus a, 3 minus 0, times the integral from 0 to 3, x squared dx, which is 1/3 times 9 by our given statement there. So f of c equals 3. Now, for this given function, this is x squared, so this means x squared, so c squared, equals 3, which means c equals plus or minus square root of 3. Now, one of those is not in our interval. That is not in this interval 0 to 3. So we're not going to worry about that value. So c equals positive square root of 3. That is the point where our maximum value is attained. All right, now the fundamental theorem of calculus, part 1. This theorem ties together two important things. That is, it ties together the derivative of a function and the integral of a function. Turns out that the antiderivative, if you take the derivative, you get the function. Okay, we've talked about this loosely, but this really ties the two things together. One particular thing we can do is we can take the derivative of an integral, and in a sense, what it does is these two cancel each other, inverse operations in some sense, and we get back this function with a change of variable based on this right here. So let's go ahead and prove this statement. So our proof. Let's begin by saying f prime of x. What is that based on the limit definition? That is the limit as h goes to 0 of f of x plus h minus f of x, capital F of x, divided by h. Well, from the statement of our theorem here, f of x is this integral, where this value is our independent value. So this is going to be equal to, I'm going to go ahead and rewrite this as limit as h goes to 0 of 1 over h. Factor that out, because this is the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt. Okay, and this is given. It's a given statement. All right, now we're going to use a property of our integral that we are given previously. Leave this one alone. A to x plus h f of t dt plus, I'm going to switch the limits here, t dt. Okay. Integral property is how I know I can switch the integral limits of integration, and that changes my sign from minus to plus. All right, now this next is another property of integrals, and it is that we can actually combine them because they share a common point. The point A. Now, whether it's between or not does not matter. We can combine this into integral from x to x plus h f of t dt. Now, looking at this statement right here, this is actually the average value. This bit right here, 1 over h from x to x plus h. This is the average value of the function. Okay, so I'm going to make that note. Average value over the interval x to x plus h. Because the width of that would be h, which we have 1 over h. Okay, so by the mean value theorem for integrals, okay, let's go ahead and make this note here. By mean value theorem for integrals, this is equal to, or actually let's add this here. There is some c in x to x plus h such that this is equal to f of c. That is the last theorem we stated. And this is going to be the same as if you just had the limit as c goes to x. Now this is because the function is continuous. We're told f of x is continuous. So as c goes to x of f of c, which is equal to f of x. Tying that together, we have that f prime of x equals f of x. where cap f is defined as the integral, and f of x is we'll find eventually is the antiderivative, or cap f of x is the antiderivative of the lowercase f. That is what that theorem does. It ties together the integral to the derivative. All right, example 3. Find the derivative of g of x equals the integral from 1 to x of 1 over t cubed plus 1 dt. By the fundamental theorem of calculus, part 1 that we just saw, this is going to be equal to 1 over x cubed plus 1. Taking the derivative, in some sense, again, is the inverse operation. It takes away that integral sign, so 1 over x cubed plus 1. All right. Find f prime of x. We have the integral from 1 to square root of x of sine t dt. All right, this is going to require our chain rule. All right, so this is going to be sine root x times the derivative of the square root of x, which is 1/2 x to the negative 1/2. So sine root x over 2 root x. So because our limit of integration was not just from a constant to x, it's to the square root of x, we have to make sure we take the chain rule there. All right, example 5, a little different in our limits. We've got x to 2x. All right, the way we're going to do this is let's start with f of x. Let's split this into the integral from x to 0 t cubed dt plus the integral from 0 to 2x. We can split it by any value we would like. It just so happens that 0 is a convenient splitting value. Now we're going to switch integrals. We want the x limit as the upper limit. So this will be negative 0 to x, that integral dt, plus the integral from 0 to 2x, t cubed dt. Now, taking the derivative of both sides, I'm just going to mark this up. So the derivative with respect to x, we are going to have negative x cubed. All right, and that will be plus x cubed times the derivative of 2x, which is 2. I'll actually switch something there. That is going to be 2x cubed times 2. There we go, because of our chain rule, which will then be equal to 16 x cubed. All right, so our f prime of x is equal to 15x cubed. All right, example 6. Well, you might want to cover the second part of the fundamental theorem of calculus. If f is continuous over the interval from a to b, closed interval there, and cap f of x is any antiderivative of f of x, then the integral from a to b of f of x dx equals cap f of b minus cap f of a. So we want to find the antiderivative of our integrand here, evaluating it at those endpoints, the upper first minus the lower endpoint. Now, because we can use any antiderivative, the most common choice, the easiest choice, is to choose the one where c equals 0, which means we are going to disregard the constant of integration whenever we have a definite integral. Okay, so indefinite, ooh, that is messy. All right, if we have an indefinite integral, that means we need to have our plus c on all of our answers. Okay, if we have a definite integral, we actually make the choice, the conscious choice, that c equals 0, therefore getting by that. Alright, so evaluate this. What we'll first do is find the antiderivative, or an antiderivative with c equals 0. So we'll do t cubed over 3, using our power rule from end of chapter 4, minus 4t, evaluated from negative 2 to 2. All right, evaluating that by 2, we get 2 cubed, so that will just be 8 over 3, minus 8, minus, valuing it at negative 2, our lower end point. Negative 2 cubed would be negative 8 thirds, and then that would be plus 8. All right, that would be 16 thirds minus 16, which will be equal to negative 32 thirds. So the area from negative 2 to 2 of t squared minus 4 is negative 32 thirds, which means we have more below the axis than above. But we can tie our antiderivatives together with our area. Okay, going back to that. All right. Evaluate the integral from 1 to 9 of x minus 1 over root x. All right. First trick we want to pull, algebra. This will be x to the 1/2, subtracting the exponents, minus x to the negative 1/2. Finding the antiderivative of those, we get x to the 3/2 divided by 3/2, so that would be multiplied by 2/3, minus, that'll be x to the 1/2 divided by 1/2, so that is times 2, evaluating that from 1 to 9. All right, plugging 9 into that entire expression would be 12, minus, plugging in 1, we get negative 4/3, which will be a total of 40 thirds. All right, and our last question for this section. James and Kathy are racing on roller skates. They race along a long, straight track, and whoever has gone the farthest after 5 seconds wins a prize. If James can skate at a velocity of f of t equals 5 plus 2t feet per second, and Kathy can skate at a velocity of g of t equals 10 plus cosine pi over 2t, there should be a t there, feet per second, who is going to win the race? All right, well, what we need to think of here is that s of t, the position function, if we take the derivative of that, that is our velocity. And the derivative of velocity is acceleration. And the derivative of acceleration is jerk, which we're not going to worry about. What we really want to know is how far they have gone. What we want to know is s of t. However, we know the velocity function. All right. So going in reverse, this is d dt. Going in reverse from what we know, this would be the integral, would take us in the opposite direction. So if we take the integral of the velocity function, that will tell us the distance. And we know we have an ending and a starting point, so we can actually find exactly how far they've gone. So for James, the distance he has gone in 5 seconds is the integral from 0 to 5 of 5 plus 2t dt. And our antiderivative there that we're going to deal with c equals 0, is 5t plus t squared. And evaluating that from 0 to 5, which will be 50 feet. Evaluating 0 makes things real easy. All right, so he's traveled 50 feet. Now, Kathy, on the other hand, a little more tricky. Integral from 0 to 5 of 10 plus cosine pi over 2 t dt. We'll have to apply our chain rule here in reverse. This will be 10t plus sine of pi over 2t. Dividing by pi over 2, we have a plus 2 over pi sine pi over 2t, evaluated from 0 to 5. And this will be 50 plus pi halves, 2 over pi, 2 piths feet. So, in this case, Kathy has gone a little bit farther than he has. So, Kathy, of course, wins. She's gone farthest in 5 seconds. Okay, that brings us to the end of this section. Tying some very important concepts together. So make sure that you're getting all the connections. I want to make sure that you understand those, so please let me know if you have questions about that.